Good morning, one and all. Hi, I'm Vishal. I'm from Electrical and Electronics Engineering Department. I'm here to explain about successive approximation analog to digital converter, improving power efficiency and conversion speed. Here we are going to see there is the analog to digital converter that is improving the power efficiency of power and power efficiency and the speed of how much it is going to uh, how much it is going to make it very speed conversion. So here let's go into this. So, an SARADC implements a binary search algorithm to find the digital code that best represents the analog input. This algorithm requires exactly n steps to find an NB digital code. An example for an 3B ADC is shown in figure 2, where a given analog input voltage Vin is translated into to an output code given a full-scale signal range between -1 and +1. In the first step, the unknown Vin is compared to a reference V reference that is initially set to the middle of the range, 0 volts. In this example, as shown in the figure, V in is less than V reference. So the first bit is resolved as 0 and the reference is now shifted to the top of the uh, mid top of the remaining search range. Since we know that V in must be between -1 and 0 volt, the new reference is thus assessed to -0.5 volt. In the next cycle, V in greater than V reference, so the second resolved bit becomes 1, and therefore the reference voltage is now updated to -0.25 volt. A last comparison resolves the third bit, which is 0, thus resulting in the final digital code 0 to 10. Here we can see the graph of analog to digital. Here the numbers which are represented in white line, they are digital, and in words it is analog. So the blue lines, we can see that the numbering from negative to positive, negative and positive. V input from upwards to downward. So V difference as we can say V difference as x-axis, right? Yeah. The red line which 0 1 0. So it is going through high and coming down to triple one. Yes, 0 1 0. The red line marking. Here in this picture, we can see that the analog input is going through T and H, and then V input is there, then M summation, sorry, it's a summation, then V in minus V reference. So it is going through diode and logic, then again neutral digital output DAC to V reference, so, and it is again going to summation. So the cycle is going round and round, round and round. On the weekend we are getting the constant output from it. As one can see, the algorithm requires three components. First, a digital to analog converter DAC is required to generate a reference voltage V reference that is updated depending on the bit decisions. Second, a comparator is required to compare V in to V reference. Finally, logic is required to time the various operations and to store the actually obtained digital code. In addition, a track and hold T and H, T and H is said to be track and hold in is also required to sample and hold the analog input voltage prior to performing the binary search method. Here in last slide, we can see in this diagram T and H, the input is going through track and hold, and then V input is insert is generated, and then it is going to submission, right? Yes, we can see in this. So SAR ADCs are very power efficient compared to the other architectures for medium accuracies between 40 and 70 decibels of SNDR switches. A higher clock frequency FCLK is usually required such that for each of the n cycles of the SAR algorithm, distinctive clock phases are available to time the DAC, comparator, and logic activities. Hence, FCLK is usually at least n plus 1 times higher than the sample rate Fs. T and H. Essentially, the function of a T and H circuit is to sample and hold the analog input signal onto a capacitor such that it can be quantized by the SAR ADC. Afterward, shows a single-ended T and H composed of a sampling switch. Here in this diagram we can see that operation sample between uh, 2-bit and sample. So here Fs, the line we are seeing that red line arrow marks TS. Uh, Now in next line FCLK greater than or equal to of n plus 1 into Fs. So here we can see the blue marks 1 and n plus 1. The difference is time. So TCLK. In this slide we have read about that, right? Yes. Now in this picture you can see that CLK going through and the Vn is generated V input and the V output through capacitors, then my CLK mode 0 holding VDD tracking. So next one, in VDD to CLK there are ups and downs. In this graph we can say that time is taken as reference point and voltage as a mean, so y-axis. So voltage V, time S. The graph is up to down V output and V, like a sinusoidal wave form. Here CLK, V input, V output, capacitor, CLK, diode. So in V diagram we can see that VTP, V in, PMOS and NMOS, CMOS, ROL, VDD. Sampling capacitance, CS. In reality, a differential circuit can be made by making two copies of this design. Further, capacitance CS is often composed of the DAC capacitors rather than an explicit additional sampling capacitance. As shown in the figure, as long as the clock signal is CLK clock signal is high, VDD V out tracks the input V in. As soon as CLK becomes low, the input is sampled and V out is held on CS. The major limitation of an N-channel metal oxide semiconductor NMOS only switch is that it can only conduct when V in is well below VDD to VTN, where VTN is the NMOS threshold voltage, which does not allow a rail-to-rail input signal. A potential simple solution is the use of complementary metal oxide semiconductor CMOS switch. In this case, an NMOS and a P-channel PMOS device are used in parallel, as shown in figure. Could this could theoretically lead to a switch with a rail-to-rail conductivity. However, this is only feasible when VDD and VTP plus VTN. If this condition is not met, the switch will not conduct for signals in the middle of the range. For advanced CMOS nodes, this requirement can become difficult to satisfy as the supple coils tends to scale more rapidly than the threshold voltages. We have learned about the uh, analog to digital converters conversion with the power efficiency and the conversion speed. Thank you so much.